About effect of PD controller. Here, the proportional plus derivative controller produces an output signal consisting of two terms. One is proportional to error signal and the other is proportional to derivative of error signal. The transfer function of PD controller is Kp into 1 plus Td into S, where Kp is the proportional gain and Td is the derivative time. Now this is the block diagram of PD controller. This is a unity feedback system. Now let open loop transfer function of a second order system is given by G of S equal to omega n square by S into S plus 2 zeta omega n. Now the closed loop transfer function for this particular system is given by C of S by R of S equal to G of S by 1 plus G of S. For this system, S into this Kp into 1 plus Td into S into omega n square by S into S plus 2 zeta omega n by 1 plus Kp into 1 plus Td into S into omega n square by S into S plus 2 zeta omega n. I will simplify this. Kp into omega n square into 1 plus Td into S by taking the LCM S into S plus 2 zeta omega n plus Kp into omega n square into 1 plus Td S is equal to Kp into omega n square into 1 plus Td into S by multiplying S square plus 2 zeta omega n S plus Kp into omega n square plus Kp into omega n square Td into S. Now from this we get Kp into omega n square into 1 plus Td into S by S square. Taking out S common from these two terms, then we are left with 2 zeta omega n plus Kp into omega n square into Td S common plus Kp into omega n square is equal to omega n square Kp plus Kp into Td is nothing but we are taking as Kd. So this would be Kd into S by S square plus 2 zeta omega n plus Kd into omega n square into S plus Kp into omega n square. Now here Kd is derivative gain. From this closed loop transfer function, you can see that PD controller introduces a 0 in the system. Because of this, it increases the damping ratio. The addition of the 0 may increase the peak overshoot and reduce the rise time. The effect of this increased damping ultimately will result in the peak overshoot. Now here, only derivative controller cannot be used because this has certain conditions and this cannot be used in all the cases. This has to be used only in the combination, because here this would reduce the rate of change of error, but on the whole it will not reduce the error. And depending upon the situation, depending upon the case where to be applied, we choose that particular combination of controllers in that particular system, because every controller has its own conditions and implementation possibility. Now we'll see the last combination, that is proportional, integrate and derivative controller. And the combination of all these three will improve the system performance in all the aspects. The proportional controller stabilizes the gain but produces a steady state error. Integral controller reduces or eliminates the steady state error. And the derivative controller reduces the rate of change of error. So according to the situation and the system, we use that particular combination of the controllers. Viewers, if you want this controller topic in detail, please let me know in the comment box so that I can make another video in detail. But from the student's point of view, knowing controllers to this extent is enough for an examination. And the basic motive of this particular channel is to help students to easily learn and memorize. And if you find this video helpful, please like, share and subscribe, and put your comments and suggestions in the comment box so that they'll be really helpful and encouraging.